show, I'm excited to present Blink. We're a team of scientists and engineers from Boston who, along with our strategic advisors, are here to solve a problem that we've all faced. You're out with your friends having a great time, and it's time to take a photo. Man, it comes out like this, dark and blurry and grainy. Why does this happen all the time, especially in low light conditions? Why can't our cameras take pictures the way that we see the scene? Is it that our eyes are simply better sensors than our cameras? Surprisingly, no. It turns out that even the cheap CCDs and CMOS sensors on your phone far outperform the human retina when it comes to pure sensitivity to light. So then, why do we perform so well in these low light settings? Well, it turns out that your brain is far better at processing these poor quality raw signals than your camera is. In a cognitive process called perceptual learning, we're trained throughout our lifetime to pick up important features of real-world objects all around us, making our vision far more efficient. And it's been shown through various studies that it's this data-driven training that allows us to see so well in these dark environments. And this is something that digital cameras have been missing out on, this amazing biological strategy, until now. What we've done in our lab over the past year is really build a computational approach to implement perceptual learning, primarily in MRI systems. We're a medical imaging group, and that's where we started. And so we built this deep learning framework, this deep neural network architecture, to automatically process the raw sensor data into the final image with a data-driven supervised learning approach. And our proprietary method, which in the academic sphere we call AUTOMAP, combines universal function approximation with manifold learning over sparse convolutional features to dramatically improve MRI image quality, especially of low signal data, achieving accuracy improvements of more than 80-fold regularly. On top of that, AUTOMAP can characterize sensor defects and automatically compensate for them. So this work has really gained incredible traction and excitement at scientific conferences all around the world, and now we want to bring this into the commercial space with Blink, AUTOMAP for your smartphone camera, which will take images far superior to what your default camera app will be able to provide. And how do we do this? Well, it turns out that the raw sensor data only recently, in the past year or so, has been made accessible by Apple and Google and Android to all modern smartphones and their APIs. So this is really great timing. So instead of MRI sensor data, Blink processes your raw camera sensor data in an optimal way to generate the best final image or video. And there's plenty of GPU horsepower to do all this on mobile, 300 gigaflops and above, more than what we would need for real-time rendering. On top of that, their mobile deep learning frameworks are also readily available to deploy these neural networks on all smartphone devices. Now, on top of the app, we also envision expanding our market by directly implementing the Blink technology in hardware, FPGA and ASIC chips for use in DSLRs, as well as cinema quality film cameras. And as the Blink thing. Okay, so and as the future involves more and more small embedded cameras and sensors such as webcams and autonomous vehicles, Blink technology really will dramatically improve low light performance throughout, which is going to be critical for things like nighttime autonomous driving and nighttime surveillance. So really, we anticipate Blink having a huge impact on all these different sectors of digital imaging technology. And we all know that technology, in turn, drives culture. Naturally lit low-light scenes are almost non-existent in movies because of how difficult they are to do. Stanley Kubrick's legendary candlelit scenes in the movie Barry Lyndon, shown here, are one of those rare exceptions. And it's well known that he was only able to achieve that because he had a huge, insanely large aperture lens, f.7, that was specifically designed for NASA. Nobody has those. No one has those. And so Blink really has the ability to democratize this and revolutionize the way we do low-light photography and cinematography by giving the operator far more flexibility when it comes to their lighting conditions and their camera settings. And most importantly, perhaps for the rest of us, we won't have to see these pictures ever again. So we've proven our technology through rigorous testing in our lab. These aren't showing up here, but the second part shows that we've secured our IP through multiple patent filings. We've recently formed a company, and now we're ready to take on new partners to really bring this to the next level. So thank you very much, and we hope you'll join us on this adventure.
All right, thank you. Questions? Who wants to kick it off? Adrien, we're in the back. Who's first? Go.
So what does the training data look like for the consumer app, for example?
Right, so there are actually a couple different ways that we're training this. And so a lot of the details I can talk to you about afterwards. The first is basically a forward model that characterizes the sensor itself so we can generate our own training data. And the second method is to actually use a bunch of examples from real raw sensor data.
Who's next? Questions? Bjorn in the back? You got a mic in the back? Go ahead, Ira, and then we'll get you next.
Do you expect that it will work, that the training data should be different for autonomous driving or for the selfies? Like between the selfies and autonomous driving seems like very different data.
Yeah, right. I think in order to get the best performance, it's going to be best to have domain-specific training. Yeah.
One quick one. That the image that you showed at the end, was that actually representative of something through your network, or was that just an example?
Yeah, so what that was showing was the SNR improvements that we've gotten with our MRI data. So that was sort of a simulated, but it's with the same sort of SNR improvements that we've
And out of curiosity, on the MRI data, maybe this is a similar question, the training data, did you find that you weren't, how do you protect against just hallucinating features, basically? Do you have ground truth data that you're learning on then?
Right, exactly. So the image reconstruction problem is sort of a much more constrained problem than many other maybe classification tasks and such. And so we actually haven't really found artifacts to be problematic at all. In fact, what's really interesting is that when we've done our MRI system, the AUTOMAP network, that was trained purely on images of natural scenes coming from ImageNet. So it actually hadn't even seen a single brain slice before. So all those pictures that you saw there. So this is a really flexible system, and it's really taking sort of generic properties of regular images all around us.
Okay, one last question. Yeah. Go ahead, James. Or Tali. Go ahead, Tali. Either one. Yeah. Take two. Okay. Go quickly.
I'm just curious, are you familiar with the fooling problem of deep networks where you can introduce structured noise and you can fool the output of the network? I was wondering if your method is resilient to that or if you looked into that.
We haven't looked into that. I think I've quickly browsed through that paper before. I think that we could do tests and see whether or not it works. But again, the image reconstruction problem is a quite constrained problem. And there are other ways that we've thought that, we might be able to fool this network, and that really hasn't been the case.
Okay, thank you. You want to go, James?
Okay, quickly.
Yeah, quickly.
So one area where the eye is still very superior to a camera is in dynamic range. And that's often important actually for nighttime driving, right, where you have headlights which can be seen during the day, so they're actually very bright. And their brightness is still bright at night, and you need to see orders of magnitude lower lux levels from everywhere else. So I wonder, your method can't really address that, right? Or it can't.
So I think for the app, that's going to be hard to address because we're working with the raw data, right, that Apple or Google Android gives us. But certainly, if we partner with Canon or Olympus or Sony, one of these people that are actually developing the sensors themselves, we can start to get at that really fine-grained level of saying, hey, give us really all the raw voltages coming off of your sensor, and let's process dynamic ranges better.
Okay, thank you very much. Round of applause.